Hi students, this is our second video for the topic of complex numbers for the International Baccalaureate course Analysis and Approaches. In this video we're going to cover operations with complex numbers. Now, complex numbers are a closed field. That means that any operation performed on complex numbers is going to result in a complex number. So we can say if we've got two complex numbers, then the addition, subtraction, multiplication and division of those numbers will be a complex number. Now the real and imaginary parts of a complex number cannot operate with one another. So for example, 2 plus 3i cannot be simplified. But real parts can be added and subtracted, and imaginary parts can be added and subtracted. So if we have z1 is equal to a1 plus b1i and z2 is equal to a2 plus b2i, then the addition of those two complex numbers, we add the real parts and we add the imaginary parts. Here's an example. 3 minus I plus 2 plus 2i is going to be 5 plus I. And it's the same with subtraction. So if we've got 3 minus I take away and then in brackets 2 plus 2i, we're going to end up with 1 take away 3i. With multiplication we just use FOIL. So we're going to have 6 take away 4i plus 3i take away 2i squared. And remember, I squared is negative 1. Collecting real and imaginary parts, we have 8 minus I. We can also find powers. So this would be 1 take away 2i plus I squared, which is negative 2i. Let's do one more. Let's expand and simplify 1 plus 2i multiplied by 1 minus 2i. You can see that it's a difference of 2 squares. So we're going to have 1 take away 4i squared. I squared is negative 1, so that's equal to 5. This one here is purely real. The conjugate of a complex number, z equals x plus yi, is z asterisk, which is equal to x minus yi. Everything remains the same, but we switch the sign in the middle. And you'd be familiar with this term conjugate from your work with irrational numbers and surds. The additional product of a conjugate pair of complex numbers is a real number, and we just saw that in the last question. Z plus its conjugate is equal to 2x. Z times its conjugate is equal to x squared plus y squared. Now there are some important results with conjugates. Firstly, the conjugate of a sum or a difference is equal to the sum or difference of the conjugates, which kind of makes sense. So here we have the conjugate of a sum or a difference, and we can split that up so that it is the sum or the difference of the conjugates. Similarly, the conjugate of a product or quotient is equal to the product or quotient of the conjugates. The conjugate of a power is equal to the power of the conjugate. And finally, the conjugate of a real number is the real number itself. And I'd encourage you to go and prove those 4 results. Let's move on. The reciprocal of a complex number is found by inverting the number. So if we want to write the reciprocal of 1 plus 2i, then it is 1 over 1 plus 2i. But we tend not to leave a complex number on the denominator. So we're going to multiply top and bottom by the conjugate of that denominator. On the top we get 1 minus 2i. On the bottom we get 1 plus 4, which is 5. This process is called realizing the denominator. And division. We're going to use the same process. We're going to realize that denominator by multiplying top and bottom by 3 plus 2i. Across the top we're going to do FOIL, and on the bottom we're going to do the difference of 2 squares. tidying everything up, we can leave it like that or split it into its real and imaginary parts. Two complex numbers a plus bi and c plus di are equivalent if and only if the real parts are equal and the imaginary parts are equal. So let's find the values of x and y if 2xy plus 3i is equal to negative 6 plus xi. You can probably see from there that x is going to be equal to 3. And then equating the real parts, 2xy equals negative 6. Substituting x is equal to 3 and solving that equation, I get y is equal to negative 1. So we saw before how to find the square of a complex number. We also need to find the square roots. Let's look at this example. Find the square roots of 3 plus 4i. So I'm going to start by letting 3 plus 4i equal x plus yi all squared, and x and y are both real numbers. Now expanding that out, we're going to equate the real and the imaginary parts, and we get two equations. X squared minus y squared is equal to 3, and 2xy is equal to 4. And rearranging that, we get y is equal to 2 over x. That's our second equation. Now we're going to substitute this into this. And expanding and multiplying everything by x squared, I have a quartic equation. X to the power of 4 minus 3x squared minus 4 equals 0. And we can factorize this equation. X squared minus 4 multiplied by x squared plus 1 is equal to 0. When I solve, I get x is equal to plus or minus 2. I don't need to solve x squared plus 1 equals 0 because that would result in imaginary answers, plus or minus I, and x is real. Now let's substitute into our second equation. When x is 2, y is 1. When x equals negative 2, y is negative 1. So the square roots are 2 plus I and negative 2 take away I. And remember, you can always check your answers by squaring them. Okay, we're going to finish off this video by returning to polynomials. So remember, a polynomial is an equation of the form p of x is equal to an x to the n plus an minus 1 x to the n minus 1 plus dot 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 plus a1x plus a0, and n is the degree. Now we learnt about real polynomials. That's when all these coefficients are real numbers. But if one or more of those coefficients is not real, then p of x is called a complex polynomial. Now we know that a quadratic equation can have 1, 2, or no real roots, and they correspond to the x-intercepts on a real number plane. But here's the thing, a quadratic equation will have exactly 2 complex roots, because complex numbers can't be displayed on a real number plane. That leads us to the fundamental theorem of algebra, which states that any polynomial of degree n has exactly n roots. There's another way that we can write it. Any polynomial of degree n is reducible to exactly n factors. Here's example 1. Find the two roots of x squared minus ix minus 1 is equal to 0. We're just going to use the quadratic formula. So x is equal to I plus or minus the square root of negative I all squared, take away 4 times 1 times negative 1, all over 2 times 1. And tidying that up, we have I plus or minus root 3 all over 2. And example 2. Factorize z cubed plus 3z squared plus 2z plus 6 over the set of real numbers. Now we could do this by long division, but it's actually much easier just to factorize by finding a common factor of the first two terms and then a common factor of the second two terms, like this. Now we can see z plus 3 is a common factor of both, and there's the factorization. So that's factorizing it over the set of real numbers. If we want to factorize over the set of complex numbers, then we need to factorize this, z squared plus 2. Do you remember how we did that? Instead of the plus 2, we're going to write it as minus 2i squared, and then do the difference of two squares. So the full factorisation is z minus root 2i, z plus root 2i, z plus 3. And here's another theorem for you called the conjugate root theorem. Complex zeros of real polynomials occur in conjugate pairs. Example 1. Find a quadratic equation ax squared plus bx plus c equals 0 if the complex conjugate roots are -1 plus or minus 3i. Now you can do this. X take away -1 plus 3i in brackets, and then multiply that by x minus -1 minus 3i in brackets equals 0, and then expand it, and you'll get there. But it can be easier to use the sum and product of the roots. So let's revise that. Recall the sum of the roots is equal to -b on a, and the product of the roots is equal to c on a. So let's start with the sum of the roots. It's -2, so -2 is equal to -b on a. The product of the roots is equal to 10, and so 10 is equal to c on a. Now this is really easy. We're just going to let a equal 1, so c will be 10 and b will be 2. Therefore, a quadratic equation which has those complex conjugate roots is x squared plus 2x plus 10 equals 0. Let's finish off with a past exam question. Consider p of z is equal to 4m take away mz plus 36 on mz squared minus z cubed. Z is a complex number, m is a positive real number. Given z minus 3i is a factor of p of z, find the roots of p of z is equal to 0. So we know that if z minus 3i is a factor and p of z is real, then z plus 3i is also a factor. So we can write p of z like this. I've got some coefficient out the front, z minus 3i multiplied by z plus 3i multiplied by z minus k, and that one is going to be a real factor. Let's expand that out, and we end up with a multiplied by z cubed minus kz squared plus 9z minus 9k. So now let's equate coefficients of like terms. We can see that a must be equal to -1. Let's rewrite that. Now let's look at the coefficients of z. -9 is equal to -m. M must be equal to 9. And then finally, 9k must be equal to 4m. So k is equal to 4. That means the roots are 4 and plus or minus 3i. Okay, that's it for this lesson. In our next lesson, we're going to look at geometry in the complex plane.